Hello class, we're going on to our next section, 10.3, using chords. So this is where we will find different arc lengths, finding different segments, using diameter, and definitely knowing, talking more about congruent circles and those chords in order to find different segments. So we're first going to go through our definitions, and I already had these kind of pre-written, and I'm just going to talk through a couple of them, and I'll fill out some towards the end of the section. But we have a chord, which is a segment whose endpoints are on a circle. And so remember, if we were to draw a picture of a chord on a circle, we would have a chord going from one end to the next end, or this could be a chord as well, that's another chord. But this time it does not necessarily pass through center. And an arc is usually the angle that's on the edge of a circle. So if I have a circle from one point to the next point on the edge, that is called an arc. And then we have diameter, which is like a chord, but it does contain the center. So those are our three definitions that we're going to use in order to solve for missing arcs and segments. So we have our first theorem that's going to help us, and it's the congruent corresponding chords theorem. In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent as well. So for example, if we have minor arcs, AB is congruent to CD. So these are our minor arcs that are on an edge. They're congruent if and only if the chords that I have here, A, B, and CD, are congruent as well. So this is where it's in the same circle, but you can also have it on congruent circles. So in congruent circles like these, I want to find the arc of FG. So I have P, center P is congruent to center Q, and then I have chord FG is congruent to JK, and I have the measure of arc JK, so here is 80 degrees, and so I need to find arc FG, but since these two are congruent to each other and they share very similar centers and chords as well as a radius, that means that FG must also be 80 degrees according to the congruent corresponding chords theorem. So that's just one example, and note you can always pause at any time in order to write what you need to. But I'm going to continue on to the next page. Our next theorem is the perpendicular chord bisector theorem. So this is where if I have a diameter of a circle and a perpendicular to a chord, then the diameter bisects the chord and its arc. So this is where I kind of create a perpendicular bisector. So I know that if these are perpendicular to each other, then the chord and its center is also going to kind of act like a midpoint. So that's how we have the perpendicular bisector part. And it's a chord because it does not necessarily pass through the center. So for this example, let's say we had a circle. So this is where I'm going to do them with you. Let's say I had a circle. No, it is not drawn to scale. And let's say we had a diameter. And we're going to call this point N. Let's say that this edge is 70 plus x degrees, and it's between J and K. We have this arc to be 11 x degrees, and then we have a point here that's called M. This is our center. And then we have H on one side and L at the bottom. And we have one part of this chord is 7, measure of 7. So let's say we want to find HK. Well, HK is pretty much our diameter. So this side is 7, the other side is 7, which makes this a length of 14. So then, let's see if you want to find the arc length of HK. So note, the arc length of HK, this is not necessarily your center. M is your center, so I drew it a little off, and that's okay. But we're trying to find the arc length. So if we want to do that, we know the measure of HJ, arc length HJ, is going to be congruent to the measure of JK. So we're saying that these two are congruent to each other if this makes a perpendicular bisector. Okay, so these two should be congruent. So I set my equations 11x equal to 70 plus x. And if I were to subtract x from both sides, I'm left with 10x equal to 70. When I divide by 10, x equals 7. So now if I want to find hk, well, hk is (70) plus 7, which gives me 77. Okay, so that means that this is the same, and so when I want hk, all I have to do is double it. So now I have 77 times 2, which gives me 154. Okay, so we said this was 77 and this was 77. If I want hk, it is not the semicircle, so it's not 180, and so that's how I get 154. Out a bit. So that is the perpendicular chord bisector theorem. So let's go on to our next one, which is the converse. So very similar. So if I'm given the sides first, or QS is a perpendicular bisector, then QS is a diameter of the circle as well. Okay? So this is what we are calling the diameter. Alright, so this is kind of just reversing it if we wanted to solve for a different length. But let's go on to our next one, 10.9 theorem, which is equidistant chords theorem. And remember, equidistant sounds very much like equal distance. And so, in the same circle or in congruent circles, you have two chords are congruent if and only if they are equidistant from the center. So, for example, if I had a circle, not drawn to scale, and I had two chords. I have chord AB and I have chord CD. And then here I have Q, and these two are congruent to each other. I kind of just redo this one a little differently. And let's say this was 12. Alright, so say if I wanted to find CD. Well, CD is congruent to AB. And so if So if CD is congruent to that, and AB, or part of AM, this part is 4, that means MB is also 12, so I have 12 plus 12, which gives me 24. So CD and AB are both 24. And then, if I want to find QM, let's say QM right here is x plus 3. Okay, and then we will say QN is 2x plus 1. So I have those two equations there. Let's say I want to solve for x, or I want to find the radius. So let's say we want to find radius of center Q. I know Q is a little off center, but we're going to say that it is. Okay, so I have QN is congruent to QN. So that means that 2x plus 1 is equal to x plus 3. So I'm left with x equaling 2 when I solve it out. I'm not going to go through the algebra because I know you guys know how to solve for x. So I have x equaling 2, and so now I can create kind of like this dotted line here. And so I have x plus 3, 12, and I can find my radius here at AQ. Okay, so I have 12. If I were to plug this back in, I get 5. So I have 12 and 5, and I can use Pythagorean theorem to find the radius. So remember, Pythagorean theorem is a squared plus b squared equals c squared. And again, you can always type this out right in the calculator. We are finding the hypotenuse, so I'm going to add my parts together. So I have 12 squared plus 5 squared, and I'm left with square root of 169, which is 13. So my radius is 13. And so that's the way you can find the radius, or if you wanted to find the measure of two chords. Okay? So that's another example, and we're going to go to the next page where we talk about our examples and our extra practices. Okay, so extra practice, we have 1 through 4. So let's see, we're talking about number 1, so we have WX. We're trying to find WX. And we're talking about the arc, not the distance. We're trying to find this. And well, if this is 42, we know by vertical angles. So by vertical angles, if this is 42, this is 42, and anything from the center out, as we learned in 10.2, the arc length is also going to be the same. So this is also 42 degrees. We wanted to find YZ, so the measure of YZ. So we're talking about this distance. Well, we have WX. So WX is congruent to YZ. So if YZ is, or WX is 3.6, that means YZ is 3.6. Number 3, we have WZ. We need to find WZ, and we're talking about the measure here. Well, this is very similar to XY. So XY is 9.2. So that means WZ is 9.2. And then our other example, we have to find the measure, the arc length of XY. So we're trying to find this part. But note, anything around Q, this is a semicircle. If I want to cut it around, so I can take 42, I can subtract 42 to get the rest of my arc length. So if I have a semicircle, so 180, minus my WX, I get 138 degrees. All right, so I'm going through these kind of fast just due to time. So we're going to move on to number 5. So number 5, we're using perpendicular chord bisector theorem. And so we know that these two are going to be congruent to each other, the chords are. So all I have to do is set my two equations equal to each other. So I have 2x minus 4.1 equal to x minus 0.5. And so I'm going to subtract x from both sides. And so I'm left with x minus 4.1 equal to negative 0.5. Going to add 4.1, and I'm left with x equaling 3.6. And I can actually do the same thing to my other side. So in this case, I have 3x minus 5 equal to 2x plus 1. So see if you can get your answer for number 6 on your own. Going to 7 and 8. So 7, I can know I'm going to use Pythagorean theorems here. Alright, so in this case I have that my chords are congruent to each other. So if I want to solve, I set my equations equal. So I have 5x minus 2 equal to 3x plus 2. I'm going to subtract 3x from both sides and then add 2 to both. So I'm left with 2x equaling 4 divided by 2x equals 2. And so I'm going to plug 2 back in. So when I have 3 times 2 plus 2, I end up with both sides being 8. And if I were to cut them in half, I have 4 and 4, 4 and 4. Okay, so I cut them in half, and if I got 4, and I plugged in 2 from x to get the whole thing is 8. Okay? And so then, now I can use Pythagorean theorem to find the radius. So in this case, CP or DP. So I can use Pythagorean theorem. So I have 4 squared plus 3 squared. So I have 16 plus 9, which gives me square root of 25, and I get 5. So So let's see if you can find a similar one using our chord here. So you're still going to solve, and when you plug in x, you should get 7. So you plug in, when you solve for x, you're going to get 3. So that concludes the rest of our notes. So let's see if you solve for 3 and you can use Pythagorean theorem to solve for your radius. And hopefully you should get 12.2. But see if you still get it. Thank you so much.